Alright, now let's have a problem where we are launching something from the ground back onto the ground a certain distance. So say we have a target or something on the ground, and we have some sort of a launcher that's capable of only launching at one velocity. We need to figure out what angle to aim this thing at, theta, such that it travels the correct distance. So let's say the distance is, I don't know, 5 meters or something like that. And let's say that the launch velocity is, 20 meters per second. I need to make sure there's enough velocity. I bet you we can get there. Okay, so we're looking for this angle theta so that this works out. Alright, so once again, we have a problem where we're under the influence of gravity alone, pretty much, when we're in the air. That gravity has constant acceleration, which makes this a kinematics problem, and we can use our kinematics equations. So, now that we know that, we need to list out our knowns and unknowns. So, well, our velocity, perhaps I should call this v initial, is actually a vector in the direction theta. So it's going to have x and y components, just like our position will. So we'll have an x initial. Okay, and one more thing our picture needs that I often forget to do until this point is a coordinate axis, an x and a y direction, and what we consider the point 0. And often it works great to just put it right at the start of the problem where your initial position was. And so this is our y, positive y direction, and this is our positive x direction. And I think that'll work out great this time. So the big advantage of doing that is it makes our initial position of our projectile 0. X initial is 0 and y initial is 0. We mentioned that acceleration was gravity. Now that, of course, is in the y direction, but since the positive direction is up, gravity is negative because it points in the negative direction. So that's negative g for y's acceleration. As for x, well, once it's in the air, there's nothing that causes it to accelerate horizontally. Gravity is only vertical, so we've got 0 acceleration in the horizontal x direction. What else have we got? Well, we don't know Vx or Vy, but we are looking for theta, right? And theta is not in our equation, which is a little bit in any of, doesn't look like it's in our variables, which is a little bit troublesome because, well, if we're going to solve for it, it better be in there. But let's look closer at the launch velocity. I'm gonna draw this velocity again. So here's my v initial here, and it can be broken up like we've done before into v initial x and v initial y and v initial x. And here's theta here. So with right triangle trigonometry, we know that v initial y, I'll just write it up here, is equal to v initial sine of theta, and v initial x is equal to v initial cosine of theta. So keep in mind, we don't really know what v initial y and v initial x are because they contain the theta, which is the thing we're looking for. So we don't exactly know those. We do know, however, our final x is 5 meters away. It has to be. That's what we're aiming at. Remember, we've got to get that x to be, final x to be 5 meters away. And as to the final y, well, it came back to the ground if it's hitting that target. So y final is 0 as well. So I think we filled in everything we possibly can. We don't know how long this thing is going to take, and I don't see how we could know the final velocities. So looking at it, we only really know 3 things. We don't really know the velocities. We only really know 3 things in both equations. So, I don't know, are we stuck? It seems like we can't solve anything directly. But if you look at this, we know that these 2 times are the same. And we also know, well, the v's aren't the same, but the theta, they both of the initial velocity term are in terms of theta. So if I could get an equation from x that relates theta and t, and an equation from y that relates theta and t, that'd be 2 equations and 2 unknowns, and we could solve for theta. So let's try and do that. If I want an equation between those two, I want to use all my knowns, and I'm not interested in the final velocities. So the equation is going to be, as it often is, x equals x initial plus vx initial t plus 1/2 ax t squared. And by this very same reasoning, we will also use y equals y initial plus vy initial t plus 1/2 ay t squared. Yep. So let's plug in the zeros that we have. I love doing that. X initial is 0. Acceleration in the x direction is 0. Y final is 0. And y initial is 0. So I've got x equals vx initial t. And I've got 0 equals vy initial t plus 1/2. Let's plug in our negative g for acceleration in the y direction, t squared, and rearrange this a little bit, also canceling a t. So let's divide through by t. That gets rid of 1 because 0 divided by t is still 0. And let's also move over one of these terms, and we get vy initial is equal to 1/2 positive gt. And you can double check that. Okay. So I'm going to go ahead and solve this one for vx initial, x over like that, just so they kind of match. So look at this. We've got t in both equations, but we don't have theta. That's right. Theta is up here. We know a little bit more about vx initial and vy initial, so let's plug those definitions in. Vx initial is v initial cosine theta, and vy initial is v initial sine of theta. So we have two equations and two unknowns here, and we need to solve for theta. Now there are probably a number of ways to do this, the method of substitution, stuff like that. I'm actually going to multiply the equations together, which you are allowed to do. You can do anything you want as long as you do it to both sides of an equation, basically. So here I go. I'm going to just copy them down here. And I'm going to multiply the entire equation together. And so that means I multiply the left side and I multiply the right side. So on the left side I get this. And on the right side, the t's cancel. That's actually why I multiplied them, right? X over t times t is x, and I'm left with 1/2 gx. And so now my only unknown is theta. The problem is it's inside of two different trigonometric functions. We can't really get it out unless we employ a trick that we may remember from trig. And it's an identity that 2 sine of theta cosine of theta is equal to the sine of 2 theta. Sine of 2 theta. There we are. So if I rearrange this, I can get that. I'm going to multiply both sides by 2 to cancel out this 1/2, and I'll divide over the v initial squared, and I get 2 sine of theta cosine of theta is equal to gx over v initial squared. And there I have my 2 sine theta cosine theta, so I can rewrite this as the sine of 2 theta is equal to gx over v initial squared. So if we just solve this thing for theta, we'll be all done. So we will get that theta is equal to 1/2 of the sine inverse of g times x over v initial squared. I skipped a couple steps, but you can do it. So that's theta. Now there is one bit of a complication here, and I don't know if you remember your trig, but because of the repeating nature of sine, the sine inverse actually has, an infinite number of solutions to it, and 2 of them are actually relevant in this case. Now your calculator will only give you one answer, but we'll also have whatever answer it gives you. Your calculator will only give you one answer, but there are actually several. So let's use the calculator to come up with the obvious answer. So calculating everything inside of the sine inverse, we have this. Just looking at the sine inverse for a moment. And the sine inverse of 0.1225 is 7.036 or so. Or in other words, the sine of 7.036 is equal to this 0.1225. However, we also have another solution to this. We know that the sine of 180 minus 7.036 is also equal to 0.1225. Now you can try that out for yourself, but what it means is that another solution to the sine inverse is 180 minus 7.036, which is so, not forgetting to divide each of these by half, our two possibilities for theta are about 3.51 and an 86.4, something like that. So we got two different answers that both make sense. Now there are actually an infinite number of possibilities for the sine inverse of the number. These are the only two that make sense. Now let's see if we can figure out how, remembering that initially we were trying to figure out the angle to shoot this so that it hits the target. Apparently there are two possibilities at one velocity. Well, let's think about it. So imagine that you're shooting something, say, really fast. Helps me to think about it if it's really fast. And you need to hit a target that's not so far away. One of your options would be to aim really low. So here's the target. Here's the thing. Launcher. If you aim really low, it's going to go pew and just pretty much fall right to the ground. Because you have a really fast gun, you have to aim really low. If you aim too high, it would go really far, right? But you have another possibility with your really fast gun, and that is to aim really high. If I aim it really high with the same speed, I'll go whoa, whoa, boom, and land back down. And that's what we have here. See, we have a really small angle and an angle that's almost 90 degrees. And as you can see, those are the only two angles that could hit the target logically, right? Anything shooting past 90 degrees would never hit the target, and anything shooting lower than the 0 degrees would just go straight into the ground. So the other solutions to sine inverse don't make sense. However, anything between 0 and 90 degrees is a valid angle as long as it solves the equation, of course. So there you have it.